Welcome. My name is Jim Beatty. I'm the chair of the Ohio State University Physics Department, and I'd like to welcome you all to the 52nd Alpheus Smith Lecture. Very venerable lecture on this campus. The lecture is a tribute to the memory of Alpheus Smith. He was a former Ohio State professor, chairman of the physics department, and dean of the graduate school, and it's made possible by the generosity of his friends and family. He joined the faculty in 1909, became chairman of the physics department in 1927, then became dean of the graduate school in 1938, and retired in 1946, but did not stop. He then was president of the OSU Research Foundation until 1958, and passed away in 1969 at the age of 92. You often hear this in the biography of physicists. It's a very healthy profession. Today, I'm particularly personally pleased to have as our speaker Dr. Joseph Incandela. Joe Incandela was a graduate school classmate of mine and received his PhD from the University of Chicago in 1986. He then has worked at both at Boston University and then at CERN as a CERN fellow, a very unusual honor for an American at a European laboratory, and then at Fermilab. And he's currently the Joe and Pat Yzurdiaga Chair in Experimental Science and professor of physics at the University of California in Santa Barbara, which has a climate just like here in Columbus. Since 1997, he has been involved with the Large Hadron Collider at CERN, initially leading a construction of the large part of the tracking system for the Compact Muon Solenoid, or CMS, detector. In 2011, he was elected to be the spokesperson for CMS, and on July 4th, 2012, he had the pleasure of being one of the two scientists to announce the discovery of the Higgs boson, which he'll be telling us about tonight. Professor Incandela was among a group of scientists at CERN that were awarded the Special Fundamental Physics Prize, commonly known as the Milner Prize, for their leadership role in this monumental scientific discovery. So tonight, Dr. Incandela will speak to us on And Then There Was Mass, From the Higgs to the Unknown. Please welcome Joe Incandela.
Thank you. Thank you, Jim. Can you hear me okay? Thank you, everyone, for that. Okay, so I'm very pleased to be here. It's a great honor to be here, and I'm going to tell you about this program that we have at CERN. It took us a very long time, you'll find out, but we eventually learned something that was pretty fundamental. And it took some pretty big instruments, and this is just a picture of part of one of them. This is part of the CMS detector. It's 100 meters underground in SUSY, France, and a lot of what you see in this picture actually was built by the US and also by Ohio State, in fact. And you can kind of tell how big it is by looking at the staircases on the side. So it's not a small device, but I'll tell you lots more about this. After starting with a bit of an introduction to the physics that we do and what we're after and how we do it. And then I'll tell you what we did. So this is the field of particle physics, and if you like, a very simple way to look at it, that many people see as a simple way to look at it, is to say that we go to higher and higher energies, which allow us to go to smaller and smaller distance scales, and we probe deeper and deeper levels of, if you like, the structure of matter and how it interacts. So just to set the scales, these are some of the distance scales that are important. 10 to the minus 10 meters is about the size of an atom. 10 to the minus 14 meters is about the size of the nucleus of an atom. And then if you were to go down and look at quarks inside of atoms, you're at the scale of 10 to the minus 15 to 10 to the minus 18 meters. Very, very small. And we've probed down there. And then in terms of energy, we use as a unit of energy the electron volt. So I wanted to give you a sense of what an electron volt is. A small fraction of an electron volt is the energy associated with the motion of air, of an air molecule. If you went up to a few electron volts, that's sort of the level of a chemical reaction per atom. 1,000,000 electron volts would be the amount of energy in a nuclear reaction per atom. And the energy, don't forget, Einstein showed that energy and mass are equivalent. The energy associated with the mass of a proton is about 1 billion electron volts. So the Large Hadron Collider, the LHC, where we work. It probes down to 10 to the minus 20 meters. That's 10 zeptometers. I didn't know that the unit was zeptometers until today. So Professor Chris Hill here told me that. And if you like, that is, you talk about nanoscience, this is 1/100th of a nanometer. We're still, we don't live at that scale. We don't know what that means even, but that's where we probe. And the beams of energy, the beams that we have proton beams. I'll show you how that's done. We ramp them up to very high energy. We collide them. Each proton in the beam has an energy of 4 trillion electron volts. And that's very important to what we do. And in fact, it allows us to get equivalent energies, equivalent temperatures of what existed in the universe about a billionth of a second after or a trillionth of a second after the Big Bang. Now, over the course of about 100 years, and as a result of the discovery of many subatomic particles and many breakthroughs in theoretical physics, we developed something that we call the Standard Model of Physics. And if you like, this is something like a new periodic table of the fundamental particles, which I show here. There's a very famous Nobel Prize winning physicist who I saw when I was a student, and he gave a talk, and he put something like this on the old days when you put plastic on the machine, you know. And he put a thing on the machine that showed all these, and he said, after 100 years and tens of billions of dollars, this is all we know. But that's a good thing, because we're trying to have a very simple, we'd like to have the simplest understanding of nature as possible, and it turns out to be fairly simple. And I'll come back to this in a moment. What's nice, too, is that it's described by one simple equation. And you guys don't think that's simple? So on the left-hand side here, you see sort of 3 columns, and we call these 3 families or 3 generations, and they're made up of quarks and leptons, and these are particles with a half integer unit of spin. You don't really have to know what half versus not half is, except to know that we call them fermions, and they have a special property, which is they don't like to go into the same state. They like to be separated. And that's how you build structure. That's how atoms are built. That's how the Pauli exclusion principle comes about. And they're named after this fellow here, which is Enrico Fermi. And then on the right side, we have the particles that carry the forces between these other particles, and each other for that matter. And these particles have spin, 1 unit of spin, and they're called bosons. They're named after Satyendra Nath Bose. And I like to point this out because people wonder where the name boson comes from, for one thing, and it's named after Bose. I also like to show this because that formula is wrong, actually. And it's just so you know that if ever in the future you're asked to have a photograph, thank you very much, in front of a chalkboard, check it before you... Because I'm sure Enrico didn't write that formula. Okay. Here's another way to look at them, which shows these particles as a function of mass on a logarithmic scale. So there's a big difference between the lightest and the heaviest. The interesting thing is that really there's lots of particles here. Well, there are not so many, but there's even fewer that are really necessary. These are really the only particles we see. This is what makes up atoms. The up and down quark make protons and neutrons. You add electrons and you have atoms. So what the heck are these for? They turn out to be very important. Even though we don't see them, even though they're not stable, they actually have a big impact on the structure of the universe and how things work. And this is part of the reason we have to find them. Okay, there was one missing piece, which just disappeared. That was the Higgs. And we have a very good description of all of this. Once we include this Higgs, we can describe how all of these particles work really, really very well, except for the neutrinos, which are extremely light, and we're just beginning to unravel. But there's many things we don't know. For example, the mass of the top quark, which is here the heaviest fundamental particle, which was actually discovered in the US just 17 years ago, is equivalent to 344,000 electrons. And we have no idea really why that is. We don't know why the masses are different. And that's something we still have to understand. Okay, as I said, the Higgs boson is extremely important. I mentioned that fermions, these spin half particles, don't like to be together, and so you form things that can build states. The bosons that carry the forces are just the opposite. They like to jump into the same state. They like to lose their identity and just become part of a coherent action. And that's good for forces. If you want a force field, you want it to act, right? You want it to have a coherent effect. Well, we didn't really understand how to describe the nuclear forces very well at a certain point. And the reason for that was that they were short range. And so to use the favored kind of theoretical physics that we had that worked so well for electromagnetism, it was tricky. The equation said that the force carriers should be massless. And so for the first time in history, we had to kind of confront what is mass and what gives mass. And the guys working on this, actually it drew about 30 Nobel Prize winners over time trying to solve this problem. It was a very fundamental problem. It got many people interested. And a couple of guys came up with some good ideas in the end. It was Brout, Engler, and Higgs. And the idea they had was kind of simple. Let's assume that the equations are right, that the rules are correct, but the playing field is different than we thought. In other words, let's suppose the universe is not what we thought. Let's suppose it's not empty, but it's filled with a field. And this field is again driven by bosons, like other force fields. And this is sort of a schematic view of what this field does. It permeates the entire universe. These are these white dots. And some particles connect to it more than others. And the more they connect, the heavier they are. So this is a very cute and very simple way to give particles mass. And in particular, it gave mass to the force carriers that we needed to be massive. And then we had this idea of using it to explain mass for everything else. But this is a kind of a very bold conjecture. I mean, you don't go around every day saying, well, the universe is not what we thought it was, especially when you have no way to prove it. So for a long time, we've been trying to prove it. It's the simplest way to make everything work, but it actually introduces lots of additional problems, which I'll talk about later. And so we weren't sure it was really there. But to prove it was there, we had to find one of the bosons that make up this field. Okay? Now, what's the problem? We didn't know exactly how heavy the boson should be, the underlying bosons would be. We knew they were massive. And we knew that they were somewhere between 100 and 1,000 times the mass of a proton. That's very heavy. And that requires a lot of energy to produce. In fact, you have to recreate, as I said earlier, conditions that haven't existed since the very beginning of the universe. And in fact, we had to go back to the conditions that existed 10 to the minus 12 seconds after the Big Bang, which corresponded to 45 million billion degrees. So we had to recreate energies corresponding to 45 million billion degrees. And that's not easy. So I'll come to that in a moment, how we get to that. And as I said before, the way we do it is to accelerate protons to very high energy, collide them head-on, and at the same time then we probe, as I said before, the nano-nano scale. So what we use are a system of circular accelerators. They're in this valley here near Geneva. This is Geneva, Switzerland. These are the Alps. This is Mont Blanc. And basically the idea is you take protons, which you can get from hydrogen gas by stripping off the electron, and we accelerate them in an electric field in a circular ring. And each time they go around the ring, they get a kick. And then we have other magnets that keep them on track. Okay? And I often describe this as something like a racetrack. Cars go around a racetrack. You know how racetracks have bank turns, right? What we have is kind of a racetrack where we can control the banking. So every time the protons go around, they get a kick in an electromagnetic field that accelerates them a little bit. We adjust the strength of the magnets. It's like raising the banks a little bit, and we keep them on track, and we keep circulating them around and around and around. At a certain point, we can't adjust the banking any further. The machine, the magnets, everything reaches their limit. And then we transfer it from one circular ring to another, and we repeat the process. Okay? And finally, we transfer it into the LHC. And you can see it's a very large ring. And in that ring, which is the largest in the world, we can go to the highest energies. Okay. So the design goals were to be able to look for the Higgs in the mass range between 100 and 1,000 times the mass of the proton, and then also to search for new particles with masses up to thousands of times the proton mass. What did it take? Well, it took a long time. The first studies for the LHC were 1984. It was approved in 1994. Construction started in 1996 of the components. They began to install them in 2003, and it wasn't until 2009 that we had first proton-proton collisions. And this took actually a lot. New concepts were required in an innovation in magnets, in cryogenics, in electronics, and it was a huge worldwide effort, in fact. I should mention parenthetically that although it was built in Europe, much of the accelerator design and some of the components came from the US, came from Japan. We're actually a fairly small worldwide community, and it really took a global effort. Okay. Here's a picture of inside the tunnel. You can see the small curvature as you go around the ring. And this is actually almost 17 miles around, underground. It's about 300 feet underground. And it's like Swiss chocolate. So, what do I mean by that? The magnets in the LHC have 11 billion joules, gigajoules, of stored energy. What is that? That's enough energy to melt 12 tons of copper. And it's the kinetic energy of an Airbus A380, that's the biggest commercial plane out there, flying at 700 kilometers per hour. How much energy is stored in the beams themselves, the proton beams themselves? It's 350 million joules. And what's that? That's equivalent to 23 kilograms of TNT or 15 kilograms of chocolate. I bet you didn't know that chocolate had more calories than TNT, did you? That'll make you think. Inside the LHC, it's a pretty amazing place. The air pressure inside this 16, 17 mile long system it's all vacuum pipe, is actually, the air pressure is lower than on the moon, and the magnets are cooled with 100 metric tons of superfluid helium, so that it's colder than deep space. It's 1.9 degrees absolute. And it's the largest cryogenic system in the world. I don't have the time to go into it, but some of the vacuum technology that was used has been used for many other things, including solar panels, vacuum chambers and solar panels that are used to actually partially power the Geneva airport now. Now I'll tell you about the experiments. I've told you about the accelerator. You have to separate the two. The accelerator accelerates the particles, slams them together. Then you need something to find what comes out. And that's what the experiments do. And they're different people and different groups and different collaborations. Here's another look at the accelerator, where it is. And the three rings I showed you, the little one, the medium, and the big. And you get some sense of how big it is by looking at Geneva Airport, which can land 747s. And it's a pretty big ring. And there are 4 big experiments. There are 2 really big ones called ATLAS and CMS. Ohio State is actually involved in both of these. I'm only involved in one, so I'm not only going to talk about that one. No, I'm kidding. I'm going to talk about both. But Ohio State actually contributed to both, which is pretty rare for an institution to do. There are 2 other experiments. LHCb, which focuses on what are called beauty quarks, B quarks, and ALICE, which is an experiment that's really designed to look at not protons colliding, but heavy ions. So they do somewhat different physics. So in this lecture, I'm only going to talk about ATLAS and CMS. So let me begin with ATLAS. This is a drawing of the ATLAS detector. It's a really large, it's the largest in terms of physical size. It's the largest experiment ever built in physics. In fact, it has a weight of 7,000 tons, 3,000 kilometers of cable are involved. It's 46 meters long, so that's about 160 feet, something like this, in length, and it's over 6 stories tall. And to give you some sense of scale, those are people, okay? Now, the size and mass are really determined by what we need to measure the momentum and energy of high-energy particles. I mentioned before that the accelerator uses magnets to keep the protons, which are charged particles, on a circular track. A charged particle moving through a uniform magnetic field will be deflected and follow a curved path. We use the same thing in these experiments. We have large magnets so that when we have a collision of protons, that energy goes into producing new particles that may decay. Charged particles come out, and I'll come back to this in a moment, but their trajectories are arced, are deflected. They form curves in the magnetic field. And we're looking for potentially very high energy particles coming out. So you have two ways to do things. You can either make a detector that's very large in a medium strength magnetic field, or you can make a detector that's very small in a very, very strong magnetic field. So what Atlas has done is built a detector that's very large in a kind of a medium strength solenoidal magnetic field where they've augmented the field with big magnets around. And so in fact their detector, although it's 7,000 tons and it's extremely large, it's much less massive than CMS, which is much smaller. I'll come back to that though. But I wanted you to understand why the detectors have to be so big. This is the cavern where Atlas was installed. This is how it looked in June 2003. And this shows them installing large magnets that are way out in the outer radius. These are large toroidal magnets. And here's the picture again. And again you see a person for scale. So Atlas has 38 countries, 177 institutions, 3,000 scientific authors, of which 1,800 have a PhD and 1,000 are graduate students. And there's lots of people from OSU involved, as I said. There's Kagan, Gann, and Cass. In fact, let's see if I can get this to work. This is a film. There he goes. This is someone, KK, this is KK, right? And he's crawling through one of these giant toroids. It's not so easy. It's good to be out, though, I'll bet. Okay, so here's CMS. This is the two experiments were often described as intense competition. There's a lot of competition between us, but the reason to have two experiments is not just for competition, is because what we do is very difficult, and the results we get, we want to be sure are correct. So the two experiments work independently, and if there's a major discovery, we want to see that both of them see it. And you'll see that happened in the case of the Higgs. So CMS was interesting because it was built close to the mountains, and it took a long time for them to actually dig out the cavern because there was a lot of water. In fact, they had to freeze the ground with liquid nitrogen and excavate 1 meter at a time. And because of that, we were forced to build the detector on the surface in pieces and then lower it down, which was a big headache, but it turned out to be of great utility in the end because the thing comes apart very easily and we can access things. But here you see pieces coming down that are millions of pounds, and actually they had to be lowered with only about an inch or two clearance on either side, which was very tricky. And I didn't know how they did it, and a high school student once asked me how they did it, and then I went back and asked how it was done, and it's pretty amazing, in fact, because you see these straps here. There are 4 of them supporting this thing. Each of these straps is actually 55 1-inch thick steel cables. Each one goes to a separate reel where they control the tension and release it, and each one had an engineer monitoring it. So we had 220 engineers monitoring the descent of this thing, all Swiss. They got it bang on, of course. And in fact, here you see how we did it. We had a crane that was bigger than the building. It's the largest crane in Europe. We had to rent it like for $1 million a day or something. It was very expensive. And this is the biggest piece that was lowered, the central piece. This is 4.4 million pounds, and it has our magnet. And I told you that CMS is smaller but heavier and has a stronger magnet in order to do things. And we recycle, just so you know, we're also conscientious about the environment. So these are shells from World War II northern artillery of the Russian fleet. And we melted them down. Here's a cheerful guy. And And we turn them into our part of our detector that we use to measure energy. So I'll show you some pictures just to give you a sense of the scale. This is the last piece going in. This is what we call an end cap pre-shower. You don't need to know what that is exactly, but you can see it's kind of a big piece, right, that they're putting in. But to give you a sense of how big the detector is, which, by the way, is much smaller than Atlas, keep that in mind. The guys I just showed you are there. Okay, so it's an enormous detector, and it took us a long time to design and build. And here is the last piece, the central tracking system going in. But like Atlas, there's about 40 countries, a couple hundred institutions. We have 2,200 scientific authors, 1,400 with a PhD, 800 graduate students, and lots of people from OSU. Here's the OSU group who were involved in lots of the muon system here and something called the CFEBs, which you can ask them about. We've also gone, Chris and I have gone to Congress to, it costs a lot of money to do this. You have to ask Congress very nicely. And here's the group. Newsweek called it the biggest experiment ever, and in parentheses, it's European. I just wanted to point out, don't ever believe anything you read, because, first of all, this is CMS, which is smaller than Atlas, so this is not the biggest one ever. And everything you see here was built in the United States. Someone pointed out last time I showed this that Newsweek went out of business, so okay. Are they back in business? Okay, very good. Hopefully they get it right next time. Okay, so this is a cross-sectional view of the detector, and I want to use this to show you a little bit about how these detectors work. You can see concentric cylinders, I think. Lots of cylindrical structure, right? So I'll do a little schematic. Hopefully this works. This is a little cartoon of how it looks. Get rid of the actual detector. And what you see is this is a very schematic way of explaining how the thing works. So in the central region, we have a very strong magnetic field. If a particle is charged, its direction will get curved one way or the other, depending on the sign of the charge. If it's plus or minus, it'll curve different ways. So we get the sign of the charge, and how much it curves, okay, is directly, inversely proportional, rather, to its momentum. So if we can measure that curvature extremely well, we measure its momentum to very high precision. And we can do that with incredible precision. We actually can measure we have many layers. I'll show you in a picture in a minute. We use these semiconductor detectors. We get little charge points, and it's kind of like we connect the dots to get the tracks. But we can actually measure where the particles cross the detectors with an accuracy of, in some cases, 1,000th of an inch or even a 10,000th of an inch. Then, so this region where we're tracking the particles, we built something that's extremely lightweight because we don't want to screw up their paths. We want to measure their paths without deflecting them. So this has to be all extremely lightweight, extremely fast electronics. When we're done with that, we hit them with really heavy things. So in this case, we have, in CMS, we have very heavy lead tungstate crystals, and followed by lots of brass and then steel and things like this. And the idea is then to stop the particles, and while they're stopping, they shed lots of light. And we bring them to a complete stop, we measure this light, and that gives us a way of measuring their energy, total energy. Okay? And so here you see a picture of the many layers of semiconductor detectors that I mentioned before. They're extremely lightweight. It looks like it's a very heavy system, but everything is super lightweight, and particles go zipping through them, and they leave charge on each layer, and then we connect the dots. And these are the lead tungstate crystals, which, quite the opposite, look very light. So they look like they're made of glass, but if you pick them up, they're heavier than lead, okay, because they're there. Oops, it's getting ahead of me, this thing. Okay, so what we do is we don't collide one proton at a time. Some people think that the experiment is we wait all day and then we shoot one proton and another proton and we're done. We're actually running continuously. This accelerator has two beam lines running two beams in opposite directions. The beams are actually made up of little bunches, about 1,400 bunches each. Each bunch has 150 billion protons, 100 to 150 billion protons, focused to a very, very fine line. And those two beams cross in the middle of our detector. And it happens every 25 billionth of a second, or 50 billionths of a second in the worst case. So it's happening 40 million times per second, and we try to do that all the time. Of course, the machine can't run all the time, but it runs, several months or more per year when you integrate it all up. Several million seconds. Now, when these bunches cross, even though there's 100 billion protons in them, even though they're focused down to something that's smaller than a human hair, protons are really darn small. So what happens is only something like 20 to 30 pairs of protons collide. So you basically don't lose anything. Out of billions, 20 to 30 doesn't mean anything. So you just keep doing this, recirculating the beam, colliding, and you wait for something interesting to happen. So this is actually something interesting. This is an event, a fairly rare event. All these yellow tracks, you see they're kind of like spaghetti. There's a lot of curvature. If there's a lot of curvature, it means it's low energy. So it's not very interesting for what we're looking for necessarily. Sometimes it is. But this is debris from lots of collisions that weren't interesting. And there was one very interesting collision that produced 4 tracks that go all the way out of the system, escape everything, even out of the heavy materials that I mentioned. And the only particles that we know that do that we would see like this are muons. So these are 2 pairs of muons that reconstruct to 2 Z particles which carry the nuclear force. And so this could be an event involving 2 Zs, which could in fact be the telltale signal of the Higgs. Higgs can decay to 2 Zs. Okay, so if you think about these detectors, they're like really giant, ultra-fast digital cameras, 3-dimensional cameras in fact. We have 40 million collisions per second, so they have to respond very fast. These detectors have to be able to take 40 million pictures per second, and they can, low-resolution pictures. We have about 76 million channels of tracking system electronics that measure the trajectories, another 4 million to measure their energy. So it's like a camera with 100 million pixels, roughly speaking. And it has to be done very fast. We have to make a decision very fast. There's so much information coming off the detector that if we took 40 million pictures per second, we couldn't possibly store all that. In fact, we can only handle about 500 per second. And so we have to select out of the 40 million which are the best 500. And that's an extremely difficult thing, and it takes really a dedicated brain that's 3 stories tall in our counting room that makes these decisions. All right, and there are a few other challenges. I want to tell you one other thing. We call it pileup. I mentioned that when these bunches cross, 20 to 30 pairs of protons collide. And we're looking for very rare events where something very interesting happens that, for instance, in the case of the Higgs, it's 1 in a trillion, roughly, collisions, or 1 in a billion, let's say, depending on what you're looking at. But that means most of them are not interesting. And if you have 20 or 30 that happen at the same time, and you're very lucky if even one of them is interesting, and the rest just produces a lot of debris in the detector. So I'll show you what that looks like. If you're looking like the beam would, down the beam line, and looking at particles going out sideways from the collision, this is what an event looks like when there's like 1 or 2 protons colliding, okay? So this is the background to what you'd see. This is what kind of tracks. These are real events, in fact, from Atlas. This is what it looks like when you have 5 to 10. And this is what it looks like for most of our data when you have 20 or 30 collisions. So you have all of this noise, okay? So we have to filter that out. If you look from the other direction, this is looking like the way the beam would look into the detector, so it sees the detector from the side. Now if you look at it, the beam line itself, this is a real event. And you see there are 20 collisions. Each one has its own color. And you see all that. These are real particles coming out. So it's challenging to pick out some rare events when you have this kind of activity going on. But we managed to do that. And we end up with tons of data. And there's so much data, in fact. In 2011, we collected raw compressed data in a quantity of petabytes, 22 petabytes. That's 22 million gigabytes. And then in 2012, it was 30. And these are the largest data sets that had ever existed. And we had to ship them all over the planet, basically. So we created a grid of computers. We have 250,000 computers in 35 countries that absorb all this data and analyze it. And our graduate students and postdocs and so forth analyze the data. And we've set up a very nice system where they can just submit jobs. They don't have to know exactly where the data is. The system finds it for them and analyzes it and returns them the answer. Okay, let me move on then to the discovery. How am I doing for time? Okay. So, how do we find the Higgs? Do we see the Higgs? Do we make them? Does it sit there? We get a pile of them? No, actually, they don't live very long. We find them by what they decay into. We can predict what they'll decay into. I showed you an event that had 2 Zs decaying to 4 leptons. Actually, it had 4 muons. Muons are types of leptons. Higgs can decay in many ways. These are 5 of the main channels. It can decay into 2 photons, 2 Ws, 2 taus, 2 B quarks, very tiny rates. But the ones I'm going to tell you about are these 2. These are kind of important because we can reconstruct, from the information in this decay, we can reconstruct the mass of what decayed. So now we can look for events that have 4 leptons in the final state, reconstruct them to 2 Z particles, reconstruct those to something, look at the distribution of all the masses, and if there was something new, we'd see a bump where we've accumulated many events corresponding to one specific mass. Do you understand? Is that okay? You can do the same thing with the photons. It's kind of like imagining something breaks apart, you know the momentum of the things. It's basic kinematics. You can do a little forensic work and reconstruct what it might have been if it was really one particle. Now, for example, in the case of photons, there are many ways in these events a photon can be produced. And it's not necessarily coming from the decay of a particle. It could be radiated off of a quark or any charged particle, and that can happen with 2 photons. So it's quite easy to make a pair of photons that aren't coming from a single particle. And you would see a spectrum of events that's just random pairs producing a mass spectrum that falls very abruptly, because it's easier to make low energy photons than high energy photons. But if there was one particle decaying to 2 photons, you would see a bump somewhere. You'd see some excess somewhere. So that's what we looked for. This is the kind of event we saw where you see lots of junk from all those other collisions I was telling you about, very low energy tracks with lots of curvature, and then 2 very high energy deposits in our crystals, which could only be coming from electrons or photons, but there were no tracks found. That's why I have dashed lines. We saw no charged particle tracks. Electrons are charged. So these had to be photons. And if we take these 2 photons and reconstruct the mass of what they would have come from, it comes out to about 125 units. Okay? So we looked at many, many events, and sure enough, we saw a little bump. Okay, so what is this bump that we saw in this mass spectrum? What's in the bump? There's a few hundred extra events that reconstruct to a mass near 125 GeV, which is about 100 times the proton mass. How many collisions did it take to find these? 10 to the 15th. So that's how rare this is to find these guys. And Atlas saw something very similar in exactly the same place. So this is kind of already pretty exciting. We worked completely independently. We brought our data together. And I can tell you about that maybe in the Q&A session. But this is what we saw. Now, there's another way you can look. As I said, you can have a Higgs decaying to 2 Z particles, which can decay to electrons or muons. Both are leptons. You can have 4 electrons, 4 muons, or 2 electrons, 2 muons. And in this event, you see 2 electrons and 2 muons in the red. And we play the same game, but this is even more rare. And here you see in Atlas a similar case where they had 2 Zs decaying to 2 electrons in each case. And we look at many of these events. We reconstruct the mass. And this is what Atlas saw. Now, red is everything we would expect to see. We actually produce Zs, and they would make these kind of red contour. Now, if there was a Higgs that had a mass of 360, we would have seen a bump here, like this green one. But you don't see any black data points that match that. If it had been 190 GeV, we would have seen a bump here. But again, there's no data points that match that. But way down here, this is what you'd see, this blue, if there was a signal at 125, like we saw in the photons, and you see there's actually data that matches that. CMS, we did the same thing, and it's a little clearer because the scale's a little bit more focused in, and you see that we see this excess at about the right place. So this was, as in all discoveries, this was we were just beginning to see something new, and we just saw it at the level that would allow us to claim a discovery. And so we presented it on July 4th, 2012. It was shown at CERN, and then live broadcast to a conference in Melbourne, and people got very excited. You know, physicists are pretty calm, quiet guys. You know, you take them to a sports game, they'll sit there. You know, then you announce this, and they're like, eh. People got very excited. Here you can see, I thought I'd show you the time, how things evolved over time. What you see is this, in this case, for instance, the red is what you would predict as a function of time for if there were 125 unit mass Higgs. And then you see the data filling in, and you can see this is days, weeks, months going by. It's very slow. It's like watching grass grow. But what you see is the data continually follows this peak. You see? And this is now with 2.5 times the data that we had at the time of the discovery. So once we had more data, it became much clearer. And here you see it in W's. The red shows you what the Higgs would add. It's gone. It'll come back. And the rest are backgrounds. The W is a less clean, less easy channel to diagnose. But what you see is that without the Higgs, there's too much data. Okay? We can't explain it with all the other things alone. But then, in the end, you'll see in red what's predicted to be added to this from the Higgs. Come on. There you go. So it looks pretty good. We're pretty much convinced that we have it. Now, I have to tell you a little bit. I think I have this out of order. Hold on. Oh, yeah, sorry. Remember I told you that the Higgs gives mass to other particles because it's this field that permeates the universe, and the more those particles interact with it, the more they connect to it, the heavier they are. So what you would expect is that when we measure the connections of different particles to this particle that we found, that as a function of mass, you should see a linear increase in the connectivity. And that's exactly what we see. Okay, we can extract this information in a fairly complicated way that I can't explain, but that's what we get. And this is what we expect for the Higgs. And so, having discovered it and announced it in July and saying we're not sure exactly what it was, in March of 2013, I went on record as saying this is a Higgs. We don't know what kind of a Higgs it is, but it's certainly a Higgs. And actually, this came out, and it was a very busy news week in March. Actually, you may remember there was white smoke above the Vatican on the same day, and then we found this. So I think Galileo would be happy to see that. And it led to the Nobel Prize. Once we had understood it, and once we'd said it was really the Higgs, and we showed these results, we showed more results. I don't have time to go into them, and they're fairly difficult to explain. The Nobel Committee awarded the prize to Higgs and Engler. Braut, unfortunately, was an American who was the other key person, and he had died in 2011. And the Nobel Prize cannot go to someone who has passed away. It can't be given posthumously. But they acknowledged that it was, of course, because we had found it, that these guys got the Nobel. And we watched it live at CERN, and as you can tell, we were pretty happy. So it was very exciting. Okay, so very quickly, since I'm supposed to talk about what goes beyond, I'll move ahead and tell you something about the future and what we're after now. This is my crystal ball. But I have to tell you about stuff that's really hard to understand. There are these fundamental connections between particles. I'll give you an example. The mass of the W particle, which is one of the heavy particles that carries the weak nuclear force, it depends a lot on the mass of the top quark and a little bit on the mass of the Higgs. And in fact, the reason is you can write down diagrams. A W moving along can suddenly turn into a top quark, actually, and a bottom quark, and then back into a W. And this is what we call a Feynman diagram for a virtual transition. And you can do the same thing with the Higgs. A W can actually radiate a Higgs and reabsorb it. This is allowed by the Heisenberg uncertainty principle, and it looks totally nuts, but actually if we don't take this into account, we can't calculate the mass correctly. You have to do this and many other things to get the mass correct. Okay? So there are these really deep connections. You cannot separate the identity of a particle from what it can become or decay into. And this is an aspect of the quantum side of physics. It's a combination of quantum mechanics with relativity in what we call quantum field theory. But don't feel bad if you don't understand it. This is a quotation from Richard Feynman, who is one of the most brilliant scientists of the US in the last century. And he was talking about relativity here, Einstein's relativity. This must have been maybe in the 30s or 40s. He said there was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there was ever such a time. There might have been a time when only one man did because he was the only guy who caught on. Of course, that was Einstein. But he wrote his paper. That was before he wrote his paper. After that, people read the paper. A lot of people understood the theory of relativity in one way or another, certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. So if you didn't understand how that works, you're not alone. We don't have any a priori experience to understand the quantum realm. We understand the rules. We understand the equations. Some people have a better feel for it than others, but it is not something we're accustomed to from our ordinary life. Okay, but I had to tell you about that because when we calculate the Higgs mass, I showed you when you calculate the W mass, adding the top and the Higgs to the thing through these virtual diagrams is absolutely necessary to get the answer right. We do the same thing with the Higgs mass. There's a classical mass, and then you have to calculate all the additions from all the standard model particles that the Higgs could decay into, and we get the answer a little bit wrong then. All right? It worked perfectly for the W, but it doesn't work for the Higgs. In fact, we're off by a small factor. We're off by 10 to the 19th. It's a little embarrassing. And we call this the hierarchy problem. Now, what it means, it's either a theoretical or a philosophical problem in the end. And for us experimentalists, we think it's more of a theoretical problem. There's something we think that's missing. We're missing something that balances this out. These effects that we're seeing that have this huge effect on the Higgs, there must be something that cancels them out that we're not seeing. And in fact, there are episodes from the history of particle physics where exactly that happened. We didn't understand the electron, its mass, its radius. Calculations were all off. And then there was the introduction of antimatter, and the positron appeared, and suddenly all of these problems went away. Everything canceled out. Now, it turns out that in the standard model, you can also get around this if you fine-tune all of the quantities that exist, all the parameters of the standard model. But you have to fine-tune them to what, 32 decimal places? We're not used to that. Nature has never told us we had to fine-tune anything like that. Much beyond 3 decimal places, you know, the moon will eclipse the sun almost perfectly. That's just an accident. And that's sort of good to 2 decimal places. But we've never seen nature require things to be accidentally what they are to 32 decimal places. But it could be, okay? That's the philosophical problem we have. So the universe could be impossibly fine-tuned. But the alternative is you could introduce new particles whose effect cancel. And we call the introduction of new particles supersymmetry. If you like, you can think of it as adding a mirror that reflects all the existing particles and distorts them a little bit. You have, for every existing particle that I showed you early in that periodic table, we have new ones that are a little bit different. And I'll tell you what's interesting about those. You would cancel out these effects. The Higgs mass could be very stable and very small, but we have to figure out where they come from. And as I said, one possibility is this very basic symmetry that we call supersymmetry. And essentially, this mirror I told you about, it takes every fermion, and for every fermion it creates a boson. And for every boson it creates a fermion. And that's the symmetry. That's the reflection, the distortion that appears. Now there's some interesting effects of this. For one thing, we know if you look at the 3 main forces that we study, the strong nuclear force, electromagnetism, and the weak nuclear force, and you go back in time and to much higher temperatures, you find that they don't quite do much. They come close, but they don't overlap. If you introduce the supersymmetry, they actually come to a point, pretty much to the same point. And some of the most brilliant men alive say this can't be a coincidence, and they think this tells you this is possibly something real, because nature tends to start simple and become more complicated as things change. This is something that could be. This supersymmetry predicts that there's a Higgs that's below 130, and we found one at, I said 126, it's actually 125. I have to change that. We have a precise measurement now, but in any case, it's where this new idea would predict it. And the other thing is that this provides some clues to the dark side of the universe. And I'll tell you what that is. If you look at galaxies, something interesting turned up in the 1930s. You can imagine that as you move away from the center of a galaxy where it's very heavy, there's less and less connection, and as the galaxy spins, the stars farther and farther out should feel less and less pull from the gravitational center, and they would lag more and more, become slower and slower. And in fact, you would predict that the velocity curve would rise like this, but then drop. And when they actually measured it, it rose. Okay, and this is Vera Rubin, and she did a survey of thousands of galaxies and found this to be very common. And the only way we could explain it, well, there are other ways tried, but the one thing that's resisted any, that survived, is to imagine that there's some huge amount of matter that we don't see, that all the stars are kind of embedded in, and they're rotating along, being pulled by this matter that we don't see. And we call this dark matter. And now we have very strong evidence for this stuff to exist. So we have to understand it. So I'll tell you a little bit about it. For that, we have to go to the dark side. What we know now from recent measurements, including those from the Planck telescope and other things, the various cosmic microwave background experiments, is that the ordinary matter that I was telling you about, this periodic table of the elements, corresponds to about 5% of the energy in the universe. Only 5%. This dark matter corresponds to 28%. And then there's something interesting in connection to supersymmetry. Supersymmetry predicts particles that would be great candidates for what this dark matter is. Something that just sits out there that barely interacts with anything else that you can't see. And remarkably, it predicts the right amount. Roughly speaking, it predicts that the universe should have about the right amount that we see. The remainder, the other 70, 60-something% of the energy in the universe is something we call dark energy. We're not really sure what this is. It'll probably be taxed someday. Department of Dark Energy? I don't know. Or maybe not. Okay? We've been looking for supersymmetry for almost as long as we've been looking for the Higgs, and we can't find it. And the absence of it has made theorists think about alternative explanations for these things. And typically, the way they go to try and fix the problem with the Higgs is to introduce either a new spectrum of particles like supersymmetry does, that's different than supersymmetry, or to introduce new spatial dimensions. Turns out that if you add additional spatial dimensions, this 10 to the 19th can be brought down to a much smaller number. So the problem goes away. And so there are lots and lots of theories. And if you don't know what you're looking for, a Large Hadron Collider is a pretty good thing to use because it'll, in principle, produce particles from any of these theories. So we're looking for all of them. And we've been looking and looking and looking. There are hundreds and hundreds of results. We searched for new particles for supersymmetry. We have hundreds of papers. We've seen nothing but the Higgs so far. But we're coming back on the air next year at a much higher energy. And so we'll be able to look for particles at higher masses than we've ever looked. And it's in a region where we think there's a good chance we could find supersymmetry. But nothing is guaranteed. We might find something else. We'd be very happy to find anything new to try to sort out this problem with the Higgs. Okay, so that's sort of the view of everything. I have one last thing to say. I wanted to mention something about the global nature of what we do. So particle physics is very global. You can see from the colors all the different people, different countries contributing. In fact, there's more than 60 countries involved in the program at CERN. The US has the biggest number of physicists, but it's still only about 15% of the total. And in the US alone, we have 100 institutions. So you can imagine how many institutions around the world there are contributing, and every institution makes a piece of this that has to fit and work when it's all brought to CERN. So this gives me a chance to tell you, is it useful? many people ask us, well, what's the use of what you do? And to be honest, we do pure physics. Pure physics, by definition, has no application. If it had an application, it would be applied physics. But historically, just curiosity-driven physics, trying to understand the fundamental laws of physics, has had great benefits for society and for economies. And the most recent, really important one, you could say, is quantum mechanics is really what underpins all of semiconductor technology, which is the basis for transistors and planar semiconductors that are used in computers and your cell phones. And so there's always some part of basic physics that is eventually applied. What we're learning now, I don't know if there'll ever be an application. But there are interesting spin-offs. Not all wheels, okay, but for example, the coordination of so much technical information across so many countries really required some thinking outside the box at CERN. And this led to something useful. There was a proposal made in the late 1980s by a man named Tim Berners-Lee. He was in the CERN data division, and this is something he wrote in March 1989, which he said is an idea, a proposal that concerns the management of general information about accelerators and experiments at CERN. Does anyone know who Tim Berners-Lee is? Yes. What did he invent with this proposal? Not the internet. The World Wide Web. So this proposal was the birth of the World Wide Web, which has had a big impact on the world. So that was invented at CERN. A lot of people don't know that. It very likely would have been invented somewhere else had it not been invented at CERN. One of the great advantages of it being invented at CERN, which is a publicly funded laboratory, is that CERN made the software free. And so it was able to distribute all over the world. And we know the impact of that. I think it's a good thing. Anyway, this was a slight understatement. I thought the comment by his boss was also interesting. Vague, but interesting. I'm sorry, it shouldn't be vague but interesting. It's vague but exciting. I should retype that. Even so, a little bit of an understatement. So coming out of our research as spin-offs, there are actually 30,000 accelerators in the world. 17,000 of them are for medicine, and they've treated many patients around the world. In our field, we invented superconducting wire. It actually cut our power cost by 90% at Fermilab. The World Wide Web, which I just told you about, the grid, which I've showed you, that's the largest computing grid in the world. The software that's used to do that is now becoming used commercially and is being used in many, many applications. Our detectors that we use for radiation detection are used in medical imaging in ways that can allow you to diagnose problems with 1% of the previous radiation dose, many, many other things. So there are lots of things going on, and this is just showing hadron therapy, where you can use protons or antiprotons actually to target tumor cells, and this other one is PET scanning and so forth. So there's lots of useful things coming out of this, in case you wanted to know. All right, let me finish up. In summary, there was a new boson that's been found. It was 48 years since the idea was hatched. It took us 20 years to design and build the detectors, 3 years to acquire the data. It was really a generation of work by thousands. I'm not going to say it, but it was a great leap for science and breakthrough of the year in 2012, which we're very pleased. So thank you very much. Thank you.
All right, we have time for a few questions. You're going to have a very big voice, and I will be happy to repeat your question. So,
and no questions are too dumb. I have a lot of dumb questions, actually.
In the front here.
Is the Higgs field at all diluted by the expansion of the universe?
Is the Higgs field diluted by the expansion of the universe? I don't believe so. No. It's also not affected by relativistic transformations. It's just a constant. As long as the universe stays in this potential, it's what it is. It's my understanding. Question up there. The question is, are gravitons of interest at CERN? Gravitons in our what we think is kind of Newtonian gravity or Standard gravity are not, because we can't possibly detect them. But if you look at these models that I talked about with additional dimensions, they predict heavy gravitons. And we do look for them. We do look for them. Do you have a question? It's constant. The Higgs field is uniform and constant. And one of the things I didn't mention is the Higgs boson has 0 spin. And the reason for that is very important, because if it had spin 1 and it froze out the way we think it did, it has to have frozen out in the early universe, then you would have a specialized direction of space. Things would look different in one direction than others, and we know that's not the case. So if there's a Higgs field, it has to be spin 0, meaning no direction is important. Yeah, back there. No, the thing is that the comment was that the Higgs mass at 125 GeV has cast doubt on the minimal supersymmetric model, and that's kind of true. It doesn't rule it out, but the way I like to put it is that it turns out that 125 GeV, I told you that supersymmetry says that the Higgs should be below 130, but it turns out that 125 is kind of high. And so what I call the Aristotelian models, the most beautiful models, don't work. But supersymmetry can be recast many ways. And for instance, if you go just beyond the minimal supersymmetric model and add one more Higgs boson, or one more boson to the system, that mass is perfectly all right. And everything we see is perfectly all right. And we haven't looked very hard for that model. And there are other models that have to be studied. The problem is there are so many different models and they're very complicated. We just need to get after the data and look for everything we can. And something's going to turn up, and it's going to be different than what the theorists expected, which we like. We like the theorists to be confused. Keep them on their toes. You have a question?
Just a clarification. It's not the boson itself that gets massive particles. It's how the particles interact with the field itself.
Yes, which is effectively, they're interacting with the boson. No, if you think about it, it's partly, in quantum field theory, you can have fields which are, in the quantum mechanical sense, there's a probability of an energy or a density everywhere. That's all you know is probabilities in quantum mechanics. But associated with every field in quantum field theory is a quanta of the field, a particle. So to prove the field exists, you have to find the quanta. In this case, it's the Higgs boson. So there's a Higgs field is what we really care about. That's what's doing the work. But to prove it's there, we have to find the quanta, the quantum of that field, which is this particle. I refer you back to Feynman's quote.
There's a young man on your right.
Yes. Oh, very young man.
I was wondering, if considering that even though we don't know anything about dark energy, couldn't you just see the relationship of matter to energy, and then the properties of matter to dark matter, and then couldn't you find out the properties of dark energy?
Yes. Yes. Can we hire you? That's basically what we're doing, okay? But it's difficult. We think, in fact, dark energy is probably another spin 0 field, right? It has to be uniform. We don't see any funny things about the universe in particular directions. And these fields are funny. These spin 0 fields can introduce a lot of energy and drive this expansion. And they call it, what? An inflaton. An inflaton. But we don't. There are other people here that are much better at this. You're going to have to talk to there are many scientists that are trying to study this and look for it. There are many experiments to try to find some evidence of it. But I would say that my understanding is that there are less well-developed theories about it than there are, for instance, for dark matter, where supersymmetry gives you very, very good, very precise predictions of what the particles should be and how they behave. But I could be wrong. Yes?
Yeah, all evening you've been talking about finding or discovering the Higgs. But at one point you said we're pretty certain that what we discovered was a Higgs.
Right. The reason I say that is we have this problem that I told you about with the mass in the standard model. So if there was only the Higgs, we have this problem. If there was supersymmetry, these new particles come in, they cancel the terms, right? But in the case of supersymmetry, there's one particle that's very much like the standard model Higgs, and then there are at least four other Higgs bosons. Okay, so in other models there are more Higgs bosons, they're heavier, the properties are a little different, and we're looking for those as well. So it's a complicated picture. Even though the standard model is very simple, we have a lot of work in front of us because we only understand 5% of the universe at this point. Yes?
How does smashing protons produce excitations in quantum fields?
Well, what happens is when we smash protons together, Chris Hill gave a nice explanation on the NPR program this morning. We're actually not, the proton is not a fundamental particle. It's actually a bag of energy of quarks and gluons, okay? And in fact, it even contains quarks that you might not even think should be there, because when we accelerate them to such high energy, the energy that they're carrying, the energy fields that they have, are very high, and you're producing particles out of energy all the time around them, so to speak. So what happens is the two sacks of things, of particles collide. Most of the time they just go through each other and all the quarks get scattered and they generate hadrons and other kinds of mesons and baryons and just a bunch of debris. But occasionally these point particles, we think they're point particles, the quarks will interact. And sometimes a quark will interact with an antiquark, and you have basically a little matter-antimatter collision or annihilation. And you produce then pure energy. And from that pure energy you can make anything whose quantum numbers add up to 0. So you can make any particle and its antiparticle, okay? And that's something you can do. In the case of the Higgs, it's more complicated. The most common form of making a Higgs is really quite complicated, and that's why they're so rare. What happens is you have gluons. Gluons, by the way, are the particles that hold the quarks together. We're very creative with our names. But gluons are these funny particles that have no mass. They can be very energetic, and what happens is when the two protons are coming close to each other, two gluons can come near to each other, and you can radiate. One of them could turn into a top quark and an anti-top quark. Top quarks are really heavy. That means they'd like to talk to the Higgs a lot. But to generate really massive particles in one of these interactions is very hard. So to have a gluon decay to two really heavy particles is rare, but it can do that. Fused with the other gluon, which produces another top quark, then you have a triangle, okay? And at the top of the triangle, the top and anti-top quark come back together, annihilate, and produce a Higgs out of that pure energy. Because the Higgs likes to talk to top quarks, who's the heaviest particles. And that calculation seems to be bang on. It sounded like I made it all up, right? But it seems to be bang on. And that's why it's so rare, because you have to actually, in the intermediate state, make this very strange, complicated interaction. And that's how it works, okay? And it's even worse than that. If you become a theoretical physicist, you can calculate all these things, and it's a lot of fun.
We have time for one more.
Okay, there was someone back in the middle there. Yeah, go ahead.
How long will the Higgs collider be on when it comes back online?
Well, it's going to come back on at a higher energy, and we're going to run until 2018 with occasional breaks. Summer breaks, short summer breaks, long winter breaks. We have a deal with the power companies in Europe not to run during the winter. And so we're going to try to run for about 3.5 years. And we expect to have many, many more Higgs bosons detected than we have now, maybe more than 20 or 30 times. So we'll have much more information and details about the properties. And we hope with this higher energy that we discover supersymmetry, which would be a much bigger discovery than the Higgs, but a tough one, or something else new. Anyway, you've been a great audience. Thanks very much.
Every year we have the Smith Lecturer Common. We present them with a plaque that has a picture of Alpheus Smith and a list of all the distinguished people who have come before them with their name at the end. You can see, you'll have to read through this list of names. I'm sure you'll recognize many of those names.
It's very impressive. I'm bringing down the average, I'm afraid.
So thanks very much for coming. And
thank you.